Okay, I want to show you guys this derivation I did, and I was reading Ramanujan's stuff and all these theorems on Q series, and I didn't really have any tools to decipher any of that stuff to get in there and get my hands dirty. So me as a young electrical engineering student, but we did study one thing that I used a lot and kind of looked familiar to these Laplace transforms. Okay, the for example, Laplace transform of the sine function is if we take the frequency domain variable as s, it's equal to one over one plus s squared. The Laplace transform of the cosine function is s over one plus s squared, and um, and so I saw these infinite products like this, and in my favorite integral of Ramanujan, I was like, that kind of looks like if we just lined up a bunch of these um, Laplace transforms and multiplied them together. And so I kind of want to ask which function has the Laplace transform of this infinite product here. And so, to do that, you would have to use the residue theorem, Cauchy, and use a Bromwich contour. It's the special one for taking the inverse Laplace transform. Or take a numerical transform. I'm not really interested in that. I wanted an analytic expression for the function that when you integrate it, from e to the minus st times the inverse transform of this, you get this. Anyway, so there's a book that teaches you that really takes this apart and shows you how to do it. It's this book by Oxford University Press. It's like worked problems in advanced mathematical physics and applied math book. I forgot the author's name, but I've used it, so it's so useful. It shows you, just breaks down how to do all these tricky contour integrals, and it really shows you how to apply this fancy theoretical stuff to get actual results, actual answers. Okay, so since we know the poles of this function here, this our f of s right here, we know the poles of it. It will be relatively simple to use the Bromwich contour. I think I misspelled that. I don't think there's a t in there. And residue theory of Cauchy's residue theorem to ascertain the inverse Laplace transform. So, step one, let's find where are the poles of this guy. This guy up here. Where are these equal to 0? So we can solve each one for 0 and find that s is equal to, plus or minus the square root of minus 1, plus or minus the square root of minus 1 over divided by q, and so on and so on. There's an infinite number of these. Okay, so we found where the poles are. Now let's plug each of these in and find, we've got to find the sum of the residues of this at each of those poles we just found, okay? So let's calculate the residue at s equal to I. It's e to the ix divided by, let's let all these s's equal to I. So let's square, I squared is minus 1. So all these become negative, okay? Negative x the q squared, negative q to the fourth, okay? Now let's find the residue at minus I, e to the minus ix. Right? We just plug in this into here. And we plug it into the denominator too, okay? Okay, and find the next pole. And you sometimes you do a contour and you have to use either the upper half plane poles or the lower half plane or whatever. These you would need both, okay? To use the Bromwich contour, you got to have upper half plane, lower, just the whole plane. Okay, and so we're going to use the a good old Pockhammer notation. I'm probably pronouncing that wrong. And because these are just, you're going to have this in each one, and you're going to have, what's different is though you're going to have the 1 over q squared for this when you put in 1 over q for s here, you're going to have 1 plus 1 over q squared, right? Because 1 squared is 1. Okay? And so you do the same. So all you get like pairs, okay? Upper half plane, lower half plane, upper half plane, lower half plane, okay? And same thing for the q squared term. Okay, then you're gonna have 2 of these factors sitting out front here in front of the Pockhammer notation. Okay, it's just the same way to write this, just a little bit different, slightly different. Okay, now we can take these top and we can combine these using yeah, so we can use this little I think kind of version of Euler's theorem, and see, you can take a imaginary exponential, and add it to the negative and get a cosine. So for this first two, we're going to add them together and get 2 cosine x over Pockhammer notation, the same denominator. Okay, and for these two guys, you can do the same thing, but now you're going to have cosine of x over q. So you're going to have negative 2 though, because, well, not sure why you'd have that negative 2 yet. Anyway, yeah, I wonder why that negative sign came from. Okay, well anyway, so you're just combining these and you're going to get this. And so these don't really help these terms right here, because they're like not the right form we want. So what do we do to get them in the right form? You multiply the top and bottom by q, and so you multiply by q, you distribute, and you get q squared here, and you get q squared over q, and you get q squared minus 1, right? And then you get a q squared on top. So, but we don't want it like that. We want 1 minus to get the right form. So that's probably where that minus sign is going to come from, I guess. Anyway, and so you do the same thing here, but this time you got 2 terms to get in the right form. So you multiply top and bottom by q to the 4th times q to the 4th. And so that makes this q to the 4th minus 1. And then you got to do q squared, distribute q squared to this one, so q squared minus 1. So it's q squared times q to the 4th. You get q to the 6th here, okay, in this term. So after we do all that, we're going to have this, okay? Right? So that's our inverse Laplace transform of this thing right here that we start. That's what we wanted to find. Isn't that nice? We get this trigonometric function times q, which is our, less than 1. It's our base. And then divide by it, and then remember q to the 6, because that's 2 plus 4. You just add these. And so then I saw this and I wrote this, and I thought, well, wait a minute, what's the definition of the Laplace transform? It's just the integral of this, right, will give you what we started off with, which is over here. Yeah, this is what we started off with, written out in the Pockhammer notation. But it's the same thing as this. Same thing. Same thing. Okay. So we distribute this e to the minus s, and let's integrate. And do the same one for each one of these, and integrate. And so you should wind up with all these guys. And once again, we wind up with the incorrect form, and so you have to multiply through by q squared, etc. You multiply through. And so we get this guy. Once we rearrange these guys and get this interesting thing, and I don't know what it's called, and I've never seen it before in math, in any derivation, and you get this. You get 2 powers of the highest power of q in the denominator, and you get 1 for, you get like you skip an even number. It's like a truncated even number pattern for the numbers in the exponent, and you get it equal to You factor out all the s's that appear, because when you take the Laplace transform of cosine, they jump out, and well, I mean, the Laplace transform from right here of cosine is s over s squared, so that's where it comes from. It's right there. But I think this might be incorrect. I think we're leaving something out. I don't think the integral, we included that when you take the integral of the cosine, or the, yeah, I don't think we have the, yeah, this 1 over q term was supposed to be 1 over that. So I think I'm missing something here, but I think the strategy is pretty cool. How you just use the definition of the Laplace transform and apply it to the work you've just done, and you get a crazy identity here where we have this infinite series equal to these. Remember, these are both infinite products now. We have two infinite products divided one divided by the other times 2 over s is equal to this big crazy thing, infinite series, with progressively smaller or larger. No, they got to be smaller if they converge. Progressively larger. The terms get smaller. The denominators get larger. Okay, let's just leave it at that. Anyway, I thought of this in 2000, and I tried to share it with some mathematicians. I had George Andrews and some other guys. Forgot. I think Jet Wimp. I hope I'm saying their names correctly. I know I'm saying George Andrews' name correctly, but no. As far as this, somebody told me that this might be an identity of Cauchy in one of his papers. So there's that. But then I take this further and I use these because these are Laplace transforms, and there's more powerful, theorems in the world of Laplace transforms. You can use a thing called convolution of two functions, and it's equal to an integral, and it's a particular integral, and it's pretty wild stuff. But this is enough for now. And maybe you guys can find out where I made a mistake or help me out, and maybe we'll publish this thing. Who knows? Okay, this is remember, have mercy. I'm just a guitar player. I'm not a professional mathematician. I just kind of move symbols around in my spare time when I'm sick of playing guitar, which I really never am. So anyway, you guys have a good one, and we'll see you later. Well, let me know what you think. Love to hear from you guys. Bye.